What I would like to do in this video is go over the following problem. We have a piston cylinder system that consists of 5 kilograms of ammonia and undergoes the following processes in a cycle. Process 1 to 2 is this constant volume process where we start at 8 bar and an initial quality of 0.65 and we move to a saturated vapor. Process 2 to 3 is a constant temperature process where P3, our pressure at state 3, is going to equal our pressure at state 1. And we're told that for this process, the energy for heat transfer is 204 kilojoules. And then finally, process 3 back to 1 is a constant pressure process. And what we're asked to do is find the PV-TV diagrams, the network of the entire cycle, and the energy of the heat transfer for each process. So let's start with our PV chart. And with our PV chart right here, we're going to have two axes. And one of these is going to be P for pressure. The other is going to be V for volume. And in this, we're going to draw our vapor dome. And with our vapor dome, what we have is anything under this line is going to be a mixture region. So it's going to have some quality associated with it. Anything on this line to the left of this critical point right here is going to be a saturated liquid, and anything on the line to the right is going to be a saturated vapor. Now, if we're above this line, depending on the region we're on, we're going to be a superheated vapor. But when we start at state 1, we're told that we're at 8 bar and we have a quality of 0.65. So what we're going to do is be somewhere in this region right here. Let's call it, this is state 1. So we have a quality of 0.65, so we're inside this dome. And what we're going to do to go from 1 to 2, it's going to be a constant volume process. So constant volume, since our x-axis right here is volume, we're going to go straight up. And we're going to go up until we hit this line, because that is where we are a saturated vapor. And that's going to be state 2. Now, on these PV diagrams, what we are going to have are these lines of constant temperature that look like this. And everything along this line is the same temperature. So process 2, which is where we got to, and 3 is where we're going, is a constant temperature process until P3 is equal to P1. So what we're going to do is start at state 2, which is where we got to, and we're going to follow this line down until we're in line with our initial state, because they have the same pressure of 8 bar. So pressure at 1 is 8 bar, is what it's given right here, and now the pressure at 3 is 8 bar. And then finally, if we've done this right, we should end up at our first state, and we do. We have a constant pressure process. We know this is right because pressure is our y-axis, so constant pressure is a horizontal line. And we end up back at state 1. So this is what our PV diagram looks like. So now let's take a look at our TV chart. Now in our TV chart, we still have two axes. One is going to be labeled T for temperature, and the other is still labeled V for volume. And we still have this vapor dome. And process 1 still has a quality, so we know we still start in this vapor dome. And this x-axis is the same. It's a constant volume process. So we're going to do the same thing. We're going to move from state 1, which is right here, straight up until we hit the line, which denotes we're at a saturated vapor, and that's our state 2. Now, unlike the PV chart, which has this sloping line of a constant temperature, a TV chart is going to have sloping lines of constant pressure, and they're going to slope in the opposite way. So what we have are these two lines right here. This will be some pressure P2, and this one right here will be some pressure P1, but we're given what P1 is. P1 is 8 bar. Okay, so we know process 2 to 3 is a constant temperature process, constant temperature process. So what we're going to do is start at state 2 and move horizontally, because T is now our y-axis. So this is a constant temperature. And we're going to move until P3 is equal to P1. So until we hit this line of constant pressure. So that right there is going to be our third state. Then finally, we're going to follow this line. It's a process 3 to 1 is a constant pressure process. So we're going to follow this line back until we get back to state 1. So the geometry is the same, but this is the cycle that you're going to see for a TV chart. Okay, so now that we've figured out our PV and TV diagrams, let's look at the network of our cycle and the energy of heat transfer for each process. Now these two are going to be related to each other. And we're going to start by looking at the following equation. Our change in energy is equal to Q minus W. So the heat that leaves our system, or comes into our system, minus the work that leaves our system. We're going to rewrite delta E as the change in potential energy plus the change in kinetic energy plus the change in potential energy plus our change in internal energy is equal to Q minus W. Now in our case, these two are going to be 0 for this problem, and we're going to have our change in internal energy is equal to the heat minus the work. Now I'm going to write this in a slightly different way. I'm going to say that a specific internal energy is equal to internal energy divided by M. So, and I'm going to multiply M by both sides. So I'm going to have M times a final internal energy minus an initial internal energy is equal to Q minus W. So what is this? This can be applied for each of these processes. So what do we have? Well, for each of these states, we're going to have to figure out what our internal energy is. And since we multiplied it by M, this is what the thermodynamic tables will give us. Now, we're going to have to look at the ammonia table, and at process 1, at state 1, we're told that it's a temperature of 8 bar. So we go to our pressure table. In my book, it's table A14, and this is going to be a sorted by pressure and have the properties of saturated ammonia. So what that means is a saturated liquid is going to be something on the curve right here. A saturated vapor is going to be something on the curve right here. So at state 1, what do we have? We have a quality of 0.65. So let's figure out what U1 is equal to at state 1. U1 is going to be equal to this saturated liquid, so our internal energy, a specific internal energy at a saturated liquid, plus our quality, which is X, times the difference of UG minus UF. And these numbers are going to be found by going down to 8 bar and using this row. So we're going to be using these two numbers right here. This is going to be equal to 262.64 plus X is 0.65 times 1,330.64 minus 262.64. And the answer to that is 956.84 kilojoules per kilogram. Okay, so that wasn't too bad. So now let's find U2. Well, U2 is on the saturated vapor part of the curve, but we don't know what the pressure is. It's at some unknown pressure. But that's okay, because V1 is equal to V2, because it was a constant volume process. So what we want to do is we want to figure out what V1 is. Then we're going to use that to figure out what U2 is. So V1, if that doesn't make sense, just watch this part. V1 is going to be equal to Vf plus X times Vg minus Vf. So it's the same equation as this, only we're using specific volume. So this is going to be equal to, the two numbers we're going to be using are these two numbers. And this is going to be equal to 1.6302. In this table, we have to multiply it by 10 to the minus 3. Plus our quantity, which is 0.65, times the difference between these two numbers. 0.1596 minus 1.6302 times 10 to the minus 3. Now we multiply it by minus 3 instead of 10 to the third because this table is being reported as our actual value. So our actual value that we're interested times 10 to the third. So your table might not have this. You might have a 0.0015982, and in that case, don't multiply it by 10 to the minus third. But this right here is going to be equal to 0.104301 meters cubed per kilogram. Okay, so that's what our volume is. Now, what we want to do, we know that V2 is going to be equal to V1. So V2 is equal to V1. And we want to go to the saturated vapor, the specific volume saturated vapor, and we're going to work our way down. We're going to work our way down until we see where our volume is. And it looks like it's going to happen between these two values right here. So somewhere between 12 and 14 bar. And that makes sense because if you look at this, our pressure goes up. What we're going to need to do is we're going to need to interpolate a little bit. And interpolating is not fun, but you'll get used to it after a while. We're going to interpolate between 12 and 14, so between these two numbers right here and these two numbers right here, because we want the saturated vapor internal energy. So we're going to find U2, and we're going to have 0.1075 minus 0.0923 divided by, so these two, divided by 1337.52 minus 1339.56. So these two. Now this is going to be equal to, well, we want to find it at this volume, so 0.104301 minus 0.0923 divided by what we're looking for, so U2 minus 1339.56. So when you're doing these interpolations, it doesn't matter if you subtract this one from this one or this one from this one, but whatever you choose, just always do it in that order so you don't confuse yourself, because it does matter that this is going to line up with this at all times. So this 0.1075 lines up with 1337 and 0.0923 lines up with 1339. And you can see I did that right here. So U2 for me is going to be equal to 1337.95 kilojoules per kilogram. So that's great. Now, let's figure out state 3. So in state 3, we go to this region right here. And we've gone into this superheated region above the curve. So we're not allowed to use this table anymore. What we need to do is we need to go and we need to find our superheated table. So here's my superheated table. And I'm looking at my superheated table in terms of bar at the beginning. So I've taken the 8 bar that I'm looking for because I know P3 is equal to P1, which is equal to 8 bar. But there's another piece of information I need, and that piece of information is the temperature I'm looking at. So what I actually need to do is look at my pressure table and go back and interpolate again. So I want to interpolate to figure out what my temperature T2 is. And we know that T2 is going to be equal to T3 because it's a constant temperature process. So we're going to use this volume again. So 0.1075 minus 0.0923 divided by these two temperatures. So these right here, 30.94 minus 36.26 is going to be equal to the volume we're looking for, so 0.104301 minus 0.0923 divided by temperature minus 36.26. And this is going to be give me a temperature, T2 and T3 are equal to 32.06 degrees Celsius. So now that I have this temperature, I can go and look at my superheated table. And in my superheated table, I know I'm going to need to find 32.06 degrees Celsius. I'm going to have to interpolate between these two values. So U3, it's going to be interpolated, but it's going to be 30 minus 40 divided by, we're going to look at this column, so these two numbers, 1357.71 minus 1378.77. So then this is going to be equal to what the temperature I'm looking at, so 32.06 minus 40 divided by what I don't know, so U3 minus 1378.77. And then U3 right here is going to be equal to 1362.05 kilojoules per kilogram. Now I'm just going to underline my kilojoules so I can find them easier. And now we're going to try to figure out all our works and all our heat transfer for each process in this cycle. So let's look at process 1 to 2. Process 1 to 2, if we look at this, we have M U2 minus U1 is equal to Q minus W. For this first process, our volume's not changing. Work is going to be equal from a final volume to an initial volume times our pressure times TV. So it relies on this change in volume. Our change in volume is not happening, so work is going to be 0. Okay? So mass is going to be 5. U2 minus U1 is going to be 1337.95 minus 956.84, and that's going to be equal to Q. So that's what I'm looking for. And that number right there is going to be 1905.55. This is kilojoules per kilogram. This is a kilogram, so we get a unit of kilojoules. So Q12 is equal to this. And we know work 1 to 2 is equal to 0. So let's look at process 2 to 3. We're going to use the same equation. So M, now instead of 2 and 1, we're going to have 3 minus 2 is equal to Q23 minus work. Okay, we're given Q23 right here. So if we move work to this side and mass to this side, we're going to have our work is equal to Q2 to 3. So that's 204 minus 5 times 1362.05 minus 1337.95. And this work right here is going to be equal to 83.5, and again, kilojoules. So that's my work. Work 2 to 3 is equal to this. And my Q 2 to 3 was given in the problem description and is equal to 204 kilojoules. Now, finally, let's look at state P 3 to 1. So our process 3 to 1. And we're going to have our mass. We end at 1, so we're going to have 1 minus U3 is equal to Q31 minus W31. Now, for this problem, we're not given any information about what this Q is or what this W is. So we need to look at it a different way. We're going to need to solve this integral to find out what our work is. But our work depends on our final volume and initial volume. And in our case, our final volume is equal to V1. Our initial volume for this process is equal to V3. Now, we just need to figure out what V3 is. So V3 is going to need to be taken from this superheated table. And we're going to use this temperature, so 30 minus 40 over, it's going to be these two numbers. So 0.16948 minus 0.17720 is equal to 32.06 minus 40 divided by what we're looking for, so V3 minus 0.17720 is equal to 0.17107, and this is going to be meters cubed per kilogram. Okay, so let's evaluate this integral. So I'll take away this superheated table and clean it up and evaluate the integral right here. So if we look at that integral, we have work is equal to the integral from V1 to V3 of our pressure with respect integrated at dV. Now, pressure does not depend on our volume, so this integral is just going to be equal to our pressure times our volume, which is evaluated at V1 to V3. So this is equal to pressure times V1 minus V3, and that's what our work is equal to. We have to be careful with the units. The volumes that we're using are meters cubed per kilogram. And our pressure is a bar. So right now, these are going to be in units of bars meter cubed per kilogram. Well, we can solve this kilogram problem by multiplying this by a mass. So we're multiplying this by a kilogram, and we can convert our bar to a kilojoule. So if we do some math with our units, what we're going to have is a bar. We're going to have a meter cubed over kilogram. We're going to have a kilogram. And we're going to want to convert a bar to a kilojoule. So this conversion factor for a bar is going to be 10 to the 5th newtons per meter squared divided by bar. So I can rewrite this just as bars times meter squared. So I only have one level of denominators. And I know that this is going to be 1 kilojoule and is 10 to the 3rd Newton meters. And this is going to get combined a little bit. So when we cancel out everything, this bar cancels with that bar, that meter cubed cancels out with that meter squared and that meter, that Newton cancels out with that Newton, 10 to the 3rd cancels out with 10 to the 5th, and we're left with 10 squared, and kilojoules and kilograms cancel. So we're left with kilojoules, but we're left with 100 kilojoules. So our work is going to be equal to P times V1 minus V3 times M times 100 to get all the units to work right. So this is going to be 8 times 0.104301 minus 0.17107 times 5 times 100. In this work, so our work 3 to 1 is equal to minus 267.08 kilojoules. Okay, so now that we know this, we can solve for what Q1 is. So we know that Q3 to 1 is. So we know that 5 times U1 minus U3, so 956.84 minus 1,362.05 plus work 3 to 1 is going to be equal to the heat from 3 to 1. And work 3 to 1 is equal to minus 267.08. And when we solve this, the heat transfer at this process is equal to minus 2,293.13 kilojoules. So we figured out what the energy of heat transfer for each process is. Now let's figure out what the net work is. So our net work, W is equal to W1 to 2 plus W2 to 3 plus W3 to 1. And this is equal to 0 plus 83.5 plus a negative 267.08. And that's equal to minus 183.58 kilojoules. And we can check this because in a cycle, our change in energy is equal to 0 since we start and end at the same state. So for a cycle, Q is equal to W. So if we look at what Q is equal to Q1 2 plus Q2 to 3 plus Q 3 to 1. And this is equal to this plus this plus this. And if we add those all together, so 1905.55 plus 204 plus minus 2293.13, we get this is equal to minus 183.58 kilojoules, and Q is equal to W, and this checks out.